Okay, guys. So that's test one, yeah? Moving ahead, test two will be sometime next week, I reckon. Stay in lab. Is it?
Next week or 3.
Give or take, next week. It'll be here soon. Today in lab, we have the unknown lab. You will receive an unknown liquid and an unknown solid. Your job is to identify them. You will need to run an IR on each. The liquid is first need to distill it, purify it by distillation. We'll meet down here at 2:30. We'll meet down here a lot of the time. We'll discuss the lab and then we'll go up. Okay? Meet here at 2:30. Any questions about the SciFinder assignment, literature assignment? How are we doing on that? Okay, I got some questions here. Thermodynamics, kinetics, very important. Lots of it is review. Also putting it in the context of organic chemistry. Delta S, we qualitatively assess. We did a couple of those examples up there. Delta H, we will actually do calculations, quantify. Got your calculator warmed up? This alkene, simplest alkene possible, reacting with HBr to give this alkyl bromide. It's an addition reaction. We will begin reactions quite soon. That handout is going around. Everybody got one? No? Everybody have the handout? Thank you, Mark. So it's an addition reaction, HBr adding to the alkene. We'll see that. Okay. We have a line reaction here. These reactions give that. What's delta H? We need to look at what bonds are broken here. The pi bond is broken. Do you see it over here? Carbon-carbon pi bond is gone. Well, what's the bond strength of the carbon-carbon pi bond? It's 63 kcal per mole. Is that shown on the first page? I gave you some bond strengths. What is this? It says 174 kcal per mole. Got to be careful. This is for the entire bonding. That's for the entire double bond. Okay? Just the pi bond is 63 kcal per mole. That's what's broken. We're not breaking the entire bonding. The sigma bond remains. What else are we breaking over here on this side? We're breaking the HBr bond. Because it's no longer over there. It's 87. Was that in the first? Was that in the table? I think it is.
Yes.
HBr, 87. Yeah? Okay, what was formed in this reaction? We formed a new CH bond. Everybody agree? This carbon now bonded to 3 H's. Over here it's only bonded to 2. Okay? And the carbon there is a primary carbon. Or it's bonded to another. So we made a primary CH. How much is that? What's the bond strength of that? Well, 101. Does it say 101 in the table over here? Primary CH, 101, yes. What else did we form in this reaction? What other bond did we form? Carbon-bromine bond. Carbon is a secondary. Both of these are secondary. That I have 69. Is that what it says in the table? No, what does it say in the table? Actually, it says 72. Okay? I think I was looking at a different table when I did this example. Please don't be confused by that. Tables can vary a little bit. Okay? So we just added up. This was broken. Yeah? And this was formed. These are bond streams. Which bonds were stronger, the ones that were broken or the ones that were formed? Formed. These are bond strings. These are not bond energies. These are bond strings. Stronger bonds. Stronger bonds are formed. Are they more stable or less stable? Stronger bonds are more stable. Are they higher in energy or lower in energy? Lower. They're more stable. They're lower in energy. That's a stronger bond. Okay? Harder to break them. It takes much more energy to break them. That's how much it takes to break the bond. It's a stronger bond. It's lower energy. If the bond is high energy, it's sitting there going, it's ready to break. It doesn't take much energy. Boom. Okay? More stable bonds equals lower energy. Okay, what's delta H here? Is this reaction exothermic or endothermic? We went to a lower energy state. It is exothermic, yeah? What's delta H? Negative what? Negative 20 kcal per mole. Difference between 150 and 170. Negative 20. How do we know it's negative 20, not positive 20? It's exothermic. How do we know it's exothermic? Well, we made stronger bonds, which are in a lower energy state. You started out with a certain energy state, you went to a lower energy state, where did the energy go? It didn't disappear, did it? These reacted to give that plus 20 kcal per mole. It gave off. It released it. Delta H equals negative 20 kcal per mole, right? Is that right? Yes, that's what we said up there. That's delta H. What about the T delta S term in the Gibbs free energy equation? We're not going to calculate that. But entropy though, go back over here. First off, based on enthalpy delta H, is this reaction favored by delta H? Yes, it's exothermic. Favored by enthalpy. What about entropy though, the delta S term? Is it favored by entropy? Michael? Why not? We went from 2 molecules to 1. That's not favorable. Delta S would be negative. Randomness decreased. Negative. Yes. This reaction is favored by delta H, but not favored by delta S. So what about overall is it favored? This can be hard to know. That can be hard to know. We're not going to get into it that deep. We did delta H calculation. We can assess delta S. Delta G overall can be hard to determine. Okay? And for what we'll be talking about, we really don't need to.
Can we say it will be possible at low temperature? Because delta S is negative and delta H is negative, so it's possible at low temperature.
It's possible that the reaction will occur at low temperature. I'd have to think about that, but in terms of temperature, the question I would ask is, would heating help this reaction? Why would heating not help this reaction?
Because it's only possible low temperature.
It's only possible? Why is it only possible at low temperature?
I think
So
she
delta
said
S is
it's not
negative and
to-
delta H is.
Well, I know all that, but why though? Why does negative make it only possible at low temperature?
Since it's like
Then why do you, then
It's how we learn. If delta H is negative and delta S is negative, it's actually possible low temperature. I cannot explain why.
but why? I mean, okay. I need to know why. What?
Is it because if you add heat, like you can think of heat as a product in that case, and if you add heat, it's going to shift back to the reactant?
I think she was referring to the spontaneity of the ignition, of the reaction.
Okay, I can hear, the heat being released is sort of a product, and if you add heat, that's going to drive the equilibrium to the left. Yeah, that's one reason to maybe explain it, that will be why. The thing that I would look at is, which term does heat magnify in the Gibbs free energy equation? Entropy. T delta S, right? T delta temperature times entropy. So temperature magnifies entropy. Is entropy good in this reaction? No, we've already said it's bad. So you don't want to, what if you heat it, you're going to magnify a bad term. Does that sound like something you want to do here? Why would you want to make it worse by heating it? You're magnifying temperature, magnifying a bad term. You would not want to heat this reaction. Okay? Which seems to be what you learned, but you need to know why, and to explain some things. Okay, what do you want to heat that reaction? We'll talk about more of that a little bit moving forward. There's some calculations over here for you to try on your own. Right here, you can try that, and then also do it with iodine. There's a couple of questions there. I2 is an F2. I'll either send out a key for that, or we'll talk about it, including the questions on the very first page. Okay? We did one here on the other side, bottom of the other side. Okay, kinetics. Rate of the reaction. Okay? Of course, depends on the activation energy. The main thing here, this part of the handout is showing reaction coordinate diagrams, showing the energy pathway of the reaction. We have here some type of energy here, progress of the reaction, starting with reactants, ending up as products. But this system here has to go up in energy. That would be called what? The activation energy?
Yes.
Is that right? What is that? E sub A? Something like that? Some activation energy. Make the reaction take place. Then we can fall down to, here the products are more stable, so this is an exothermic reaction. If we're doing delta H, if you're coding it as delta G, then the term is exergonic. Typically, I would just stick with delta H. And this looks like an endothermic reaction. They both have activation energies. This is reactants, this is products. What exists right here, like at the very top here? Yeah, that's like some type of transition state. That's where the bonds are like being formed, right? We're going to make a bond here. Yeah? We'll make a bond. See that transition state there happening? Also, let's make a bond. I have to put energy into my arm. Here it goes. Boom, I just put energy in. The energy in my arm is going up. Yours is going up too. To highest energy, and then once the bond's made, then we can settle in, right? Arms are moving together. If they connect, then we can settle into this bond, and we, okay? There's an energy pathway there. Transition state, sometimes called the activated complex. All right, look familiar? There's some questions over here. Here we go. Which reaction is most favorable of these four? What does that mean, favorable? Which reaction looks most favorable? These two are endothermic, not favorable, right? These two look more favorable. Which one is most favorable? It's hard to say here, but I think that this is that. I think that's more favorable, right? Favorable is more of a thermodynamic term. More exothermic, more favorable.
You need to look for activation energy, but it's very small.
Well, activation energy is going to be more about which is fastest, which is the next question. Which favorable reaction is fastest? Hey, it's going to be fastest. Two separate things, rate versus sort of favorability. I don't know if you call it spontaneity. I haven't had think in a long time. I don't know what you call it these days. Exothermic reaction is called spontaneous. Is that right? Is that right? Yes. Okay, well, a diamond reacts with oxygen very exothermically. It's called spontaneous then, right? Yeah? Okay. So do you see diamonds reacting with, and there's oxygen all around, do you see diamonds just reacting with oxygen spontaneously? So why do we call it spontaneous? Because it's exothermic. The reason you don't see a diamond reacting with oxygen too easily is because, yes, it's exothermic, but guess what? I'd have to be a mile high because this is keep going, or whatnot. Okay? The activation energy is so high it just doesn't happen, even though we call it a spontaneous reaction. Is that right? All right? So the rate is so slow that it's just not observed. Down here, what do we have? Down here we have a reaction coordinate diagram where we have an intermediate. This is an alkene reacting with HBr to give alkyl halide. It's an overall exothermic reaction. There's an intermediate, and you have an intermediate energy well. And so you have a transition state leading to some type of discrete intermediate. Then the intermediate undergoes a separate reaction with another transition state. Okay? It's an overall mechanism. Sometimes these are each called two elementary steps, I think. The overall reaction consists of two elementary steps. The first elementary step leads into the intermediate, and the intermediate reacts. So we can show that with a reaction coordinate diagram. The intermediate is higher energy than the starting and the product. This reaction is exothermic. Two steps. Which is going to be the rate determining step? Rate determining step is the one that has the highest activation energy, the more difficult one. The difficult step controls the rate. So this is your rate determining step here. Then what do we call this next step? We call that fast compared to the rate determining step. So the rate depends on this step. That's called the rate determining step. If you wanted to speed up the overall conversion of this to that, which step would you focus on? The rate determining step. If you speed up the other step, you're wasting your time. Two transition states there, yeah. Next, this shows how this is actually two intermediates. And one thing this shows is typically the intermediate with the lowest energy typically has the lowest transition state leading to it. The higher energy intermediate, you have the higher transition state or activation energy leading to it. This is sort of a subtle key point here. We'll say which is going to be favored. In this case, these are cations, and this one's more stable. We can call this A and B. That's A and B. We say, okay, which is going to be formed here? And we're going to say A. And the answer would be why? Why is A formed here? You're going to say because it's... Why is A formed here? Preferred.
It's more stable.
Thank you. You're going to say because it's more stable. That's actually not correct. The reason A is formed here is because the transition state leading to it is lower. That's the real reason it's formed here. Okay? It's a subtle difference. But typically, a lower energy intermediate is going to have a lower transition state energy leading to it. All right? Usually. Not all the time. Look at this case. Here we have a two-step mechanism or process here. The first step is the same for both. From here, the intermediate can do two different things. The same intermediate can give the 1,4 product or the 1,2 product. We'll see this later on. Which is more stable? The 1,4. Based on what we said up there, the 1,4 should have the lower activation energy. Does it here? No. The 1,4 actually has the higher activation energy. So that's an exception to what we said above. Above we said that usually the lower energy intermediate, or in this case product, should have the lower activation energy. Not the case here. So there is an exception. All right? We'll see that exact reaction during test 3 material, and I'll show this again. Question, why is the 1,4 product more stable? These are two alkenes. That alkene is called the 1,4 product, this alkene is called the 1,2 product. All you got to do is look at the structure. Why is the 1,4 product more stable? What?
Different connectivity.
I can't.
Different connectivity.
So explain the different connectivity.
Your mind connected to.
And we looked at this for the first time yesterday at about 10:20, I think.
Wow.
10:25.
1025.
Okay. Alkene, how do you judge stability of alkenes? We looked at that yesterday. This alkene has, is that mono, di, tri, tetra? It's shown all condensed. Those H's are really there. That's a disubstituted alkene. That's a monosubstituted alkene. Otherwise, they're isomers. Which one's more stable? Disubstituted one, right? Okay, I refer back to yesterday's lecture at 10:25. Okay, we'll look at that plenty more time. What's on the bottom here? We have a reaction coordinate diagram where there's, how many intermediates down here? One from here, if that's a product. How many intermediates does this show? 0. There's no intermediate in that reaction. There's only a transition state, right? Some type of transition state. An intermediate will have a well, an energy well, where it settles into some discrete, okay? All right? So, should be some reading in your textbook about reaction coordinate diagrams. You will be asked to draw them like in lab reports. All right, energy pathway. And some common terminology there. Questions about that handout? You got nomenclature, need to be watching, yeah? Including, importantly, the EZ terminology, okay? And if you watch this, pay attention while you're watching it. You should find that this should be pretty easy, okay? All right? Huh? 10 out of 10. Okay. 9.5. All right. I have a tough time hearing up here. All right, y'all ready for reactions? Not sure you are. Not sure you are, but guess what?
We're going to do it today.
It's coming. It's here. Okay, reactions warm-ups. Alkene reactions warm-up. We got an alkene reacting with HCl, we got an alkene reacting with aqueous sulfuric acid, alkene reacting with bromine. What is that? Well, it's just solvent. Okay. Got green handout, yeah? We'll look at this a little bit, then we'll be moving to the white one. Here's a summary of our reactions. What type of reactions are we going to be doing? At least at the beginning? Yes, that's right, electrophilic additions. Okay, my handouts tend to have some headings here that I feel are quite important. Useful. Please recognize that. There's terminology. And these reactions involve what? What do they involve? They involve reactions with H plus as the electrophile. Please recognize my headings are meant to be informative. Organization. What are we looking at? That's the starting point, okay? Here are some reactions with H plus as electrophile. We'll react with like HX. We'll make alkyl halides. What are we making? Important. We'll convert, and we're doing reactions with alkenes. The pi bond of the alkene, those electrons are not held that tightly in the pi bond. Those electrons will react with things. Okay? All these reactions up here, they're reacting with H plus. But in sort of different other things here. That's H3O plus, that's aqueous acid. We can convert it to what? An alcohol. We can convert to ethers. Okay? We'll focus on those reactions. And first one will be addition of HX to give alkyl halides. And that's the very first reaction up here on the white handout. All right? Then we'll move below. Looks like a lot of reactions. Well, you've taken math, and it looks like a lot of math. How many addition problems could you show on the board? 56 plus 32, there's one. How about 56 plus 101? That's another. Can you do all those? You know how to do them. Okay? Don't be intimidated by all this. Let's learn the consistencies and how to do them. Okay? There's very common consistencies, approaches to doing these reactions with alkene. All right? We also have outline here. And again, the first thing we'll look at is addition of HX to give alkyl halide. And we'll start with a mechanism including rate determining step. And we'll cover this stuff. Okay, very important page here. Mechanisms. Thus far we've done acid-base mechanisms. Now we'll start doing many other mechanisms. But there will be consistencies. One thing we'll see is making nucleophile to carbon bonds. A nucleophile is something that, what is a nucleophile like? A winophile likes wine. What's a nucleophile like? Nucleus. The nucleus is positively charged. That's what it really likes. But we don't call it a positive phile or something. We call it a nucleophile. The nucleus is positive. It likes a positive. What's going to like a positive? Something that's negative. Anions are good nucleophiles. They can also be neutral. Okay? Something that's electron rich. It's almost analogous to a base. In fact, there ain't much difference between a nucleophile and a base, except when it attacks an H, we call it a base. When it attacks anything else, we call it a nucleophile. I'm sure this is written somewhere. Nucleophile can bond and make bond to carbon. It's now, okay, there's your carbon, it's now bonded. That's what we're doing here. A couple of ways this can happen. It can attack a carbocation. And that's what's happening with these electrons. Anytime you show a mechanism here, these electrons are making bonds to carbocation. Okay? This is explained here. We also have stereochemistry. What is the hybridization of the carbocation? How many H's on this carbon? Just one. Just one. It's only got 3 bonds. That's why it's a positive charge. Okay, what's the hybridization? It's sp2. How about its geometry? Trigonal planar. It's planar like a piece of paper. Okay? Planar like a piece of paper. There it is. Flat on the board. Planar. Okay? Carbon. When the nucleophile attacks it, how does it attack it? Well, here we go. It's planar. It's walking around. It's in the flask here. Okay? You're a nucleophile. You attack. Oh, okay. Keep your bond there. So your bond is now that way. All right? You attack. Oh, your bond is that way. Now this is all swimming around billions and billions. What are you going to end up with? Some bonds are on this side of the plane, and some bonds are on this side of the plane. What if we turn it up like this? How would you attack? So your bond is straight up. You're going to. Oh, your bond is straight down. You got 2 sides to the plane, and that's why you get the stereochemistry you get. This is where the nucleophile came in from the front. The bond is just projected from the front. Unless you're throwing a boomerang and it ends up in the back. But no. This is where the nucleophile came in from the back. Alright? What's going to be the ratio of these two? It's gonna be 50-50. If you flip a coin 100 gazillion times, you're gonna get 50-50 heads and tails. Okay? And that's one or two sig figs. Okay? When I say 50-50, we know that's right. Okay? I'm not saying it's 50.000000000 50-50. What does sig figs mean? Okay? But that's the outcome there, and it should be pretty straightforward. It will always be the outcome, and this is an introduction to that. There's more there. Another way to make the nucleophile to carbon is to have something there called a leading group. Leading groups leave. The nucleophile comes in here, these electrons come in here, and these leave. Or we can say the nucleophile comes in here and kicks that off. Do you see a carbocation here?
No.
No. Cation, carbon cation. There's no carbocation here. You have a leaving group instead. So there's no plus here. Something connected. Okay? And you're going to be the nucleophile here. And you're going to... How are you going to come in?
Oh, wait.
Well, the answer here is written up there. You're going to come in from the backside. Boop. You kicked me off. Now you're bonded. It's backside there. Both. Did we say both sides in this case? No, both sides was above. This comes in backside. Leaving group gets kicked off. What does this arrow right here mean to you? The leaving group takes on what?
It's electrons.
Takes on a lone pair. That's where that lone pair comes from. Arrow movement shows everything. But stereochemistry here. If the leaving group is forward, how's the nucleophile going to be? Here we go. The leaving group is forward. How are you going to come in? Well, you're going to have to come in back. Kick me off. Keep your bond up there. That new bond is now back. What if the leaving group was straight up? How would the nucleophile come in? Straight down. What if the leaving group was back? How would the nucleophile come in? Forward. Okay, so this is called nucleophilic displacement of a leaving group on a tetrahedrocarbon. It's called SN2. Those are details we haven't seen yet. What I'm really looking at here is two ways to make a nucleophile carbon bond. One of them is to attack a carbocation. When you do that, you get both outcomes. When you kick off a leaving group, do you get both outcomes? No, you only get the reverse. You get an inversion is what we're going to call it. It can only come in from opposite or backside, it's called. Okay, very important. I wish every textbook would go over this. They don't seem to do it. They just sort of give you these details along the way. But this is very fundamental to what we're doing. Very important here. Okay. I also give you some, if you want this, if you want it, it's here. It's a few introductory guidelines on proposing and showing correct reaction mechanisms. Free information, no extra charge for this. Okay? You see where it says X here? That means don't do that. Alright? This is doable. Don't do that up there. Alright? Please read. Alright, let's get ready to... Alright, we got our outline, which is green, and it's right there, and Roman numeral 1, addition of egg checks to give alkyl halides. What is this reaction known as? Also known as? Yes, hydrohalogenation. We're adding a hydrogen and a halogen. Here we go. It went around. Did it run out? Who did not get one? Did the stack run out? Here we go. This alkene, which has this formula, by the way, will react with HBr to give this alkyl halide. Specifically alkyl bromide, it's a reaction with what we call HX. X typically halogen. This can take place with HCl, HBr, or HI. Typically not HF. It's an addition reaction because if you just look at it, this formula now has HBr added to it. I mean, the molecule has HBr added to it. It's an addition reaction. There's only about 5 types of reactions in chemistry. One of them is an addition. One of them is an elimination. One of them is a substitution, which in Gen Chem you may have called replacement. Is that right? Okay. There's a couple others, but there's not many different broad types. This is an addition. What is the mechanism for this reaction? How does it take place? And we will do plenty of mechanisms. That's big thing in organic chemistry, particularly here in organic 1. First off, we know HBr is polar. The H has a partial plus charge. We talked about that. These electrons are not held that tightly. They'll be attracted to this partial positive. We can show that by saying these electrons are going to move and go make bond to H, and these move on to bromine. Now this arrow is pretty straightforward. The covalent bond here is being broken. That's moving on to bromine. That's the 4th lone pair. The bromine is now minus formal charge. What are we doing here, though? This is shown different ways. It's almost, I'll do this here. Here's your pi bond. What's happening is the electrons break free from one carbon and they sort of go and do this and bond to the H. You envision that? Okay. Someone grab my hand there and pull it up. Here's an H sitting up here. Someone visually grab my arm and pull it up there. Grab it. You're pulling me up, and I wasn't bonded. Well, what you're pulling me is right there. That arrow is dragging it up, but it's showing where it's going. Okay? It's breaking away from this carbon. Now look what we got over here. Which bond did we just form? I agree we just formed that bond. Those electrons here, it's now up here, binding to an H. What about this carbon over here? It just lost a bond. You see it no longer has the pi bond bonded to it? Well, that's a positive charge because that carbon no longer has an octet. It's only got 3 bonds. And this is a carbocation intermediate. Now, we could show it like this. HBr could be shown ionic. It's okay to start right like that. If you did that, you would do the same thing. You would just be attacking just along H+, and the Br is already minus.
Question.
Yes?
What is possible to break the bond, the double bond? What is the possible reason that the bond will break?
What is a possibility?
Yeah.
Well, it's highly possible because the electrons are held pretty loosely.
But it's
Okay.
double bond.
H plus over here,
Okay.
your H plus, okay? I'm the pi bond.
Right.
These electrons are, the pi bond is not held tight. It's a little loose, okay? And electrons, you're an H plus. What are electrons like? Electrons are negative, you're plus. Ooh. You get some attraction here. And basically what happens is, I'm sorry carbon, but I like the H plus, and the electrons just sort of move there. And lo and behold, you just made a bond. And this carbon no longer is bonded to the pi bond. And that's the transition state. Now you got the bond. The electrons are able to move.
So it can move, but it can't rotate, right?
They what?
It can move, but it won't rotate.
Oh, it can't rotate, yes. You can't rotate until it's broken. but these electrons just start bulging out or something. And okay, this is the transition state you're trying to imagine. It's good. Keep thinking. We'll do this more and more, and it will become more commonplace. The electrons move out. We made the bond, intermediate. What's next? How do we get the final product? Final product has bromine bonded here. Well, these are electrons. Electrons, negatives like positive. These electrons then make bond to the carbocation. And we just made that bond, and we're home. We're done. The first step is the pi bond. Pi electrons make bond to H. Carbocation intermediate, it's a discrete intermediate that can be observed. Then the bromide comes back and attacks. The first step is the rate determining step. Typically forming your carbocation is the rate determining step. The bromide adding is fast. Fast step. Look here, this is a nucleophile. Making a nucleophile to carbon bond by adding to the carbocation. Didn't we do that? Here we go. Did we do it? And when we do stereochemistry, it's going to add from the front or the back. Okay? The H plus is actually called the electrophile. What does that mean? It likes electrons. What type of species is going to like electrons? Something that is a positive or electron poor. Is this H positive or electron poor? There it's shown to be electron poor. Here I actually showed it as a positive. Positive things like electrons. Okay? Electrons like this. We'll do more and more. Okay, reaction coordinate diagram. Let's do that real quick. We have reaction progress. We have some type of energy. We have some type of arbitrary starting point. This is our alkene, right? What do we have? How many intermediates? One. Carbocation. You can call this A, B, and the other one C. So that's A, that's B. How does C compare to where we started? Is this reaction exothermic or endothermic? You can get your calculator out, or you can look at it. We went from a pi bond to two new sigma bonds. We made that one. Oh, what other bond did we make? Did everybody recognize that we also made that CH bond on the end? That carbon has two H's. But this carbon now has three. You got to keep track of your H's. We went from a pi bond to two sigmas. Did we go stronger or weaker?
Stronger.
We went to stronger bonds. Is that going to be more stable or less stable? More stable. Is that higher energy or lower energy? Lower energy. This reaction should be exothermic. AB, exothermic. How do we go from A to B? Straight there, or do we do something more like this? Yeah? And we have an activation energy. Then from here, do we just go straight down? No. You got to have a little activation energy, but not much. Why do we not need much activation energy? Because typically when you fall downhill, you don't need much energy. Go to the top of the stairs. All you got to do is bend your knees a little bit and go like this. You're going to fall down. It doesn't take much energy to fall downhill. This is going to be an easy, fast step, rate determining step right here. Okay, think about that. Let's try to finish up right here with an important thing to think about. This reaction is regioselective. The bromine ends up on the tertiary carbon. When you do this reaction, you do not get this product with it on the primary carbon. No. Why not? We need to think about that. We'll pick up here tomorrow, yeah. See some of you this afternoon, 2:30 right here. Unknown Lab. Distillation video on YouTube. Is that there, right? Distillation video?